Welcome back to Hancom Office Show. Unit 3, Fluid Mechanics. Contents 3.1, Introduction 3.2, Properties of Bulk Matter 3.3, Density and Pressure in Static Fluids 3.4, Buoyant Force and Archimedes Principle 3.5, Fluid Dynamics. Introduction to the Fluid Mechanics. Fluid dynamics, it's learn about a fluid motion, but fluid statics is a study about at rest. Fluid is a substance that can flow in liquid and gases. Elastic deformation is a reversible deformation. Is a reversible deformation by force applied within elastic limit. Plastic deformation doesn't regain their original shape when the deforming force is removed. 3.2 Properties of bulk matter. Stress is the force per unit area that is causing some deformation on an object, F over A. Its SI unit is Newton per meter square, is Pascal. Strain, measure of the amount of deformation by this applied stress and defined as the changing configuration of a body divided by its initial configuration. Strain, changing configuration or initial configuration. It is unitless quantity. There are three kinds of strain: tensile strain, shear stress and strain, volume stress and strain. Number 1. Tensile strain. When the end of a bar, rod or wire of a uniform cross-sectional area A are pulled with equal and opposite force of magnitude. Like tensile stress, F at the perpendicular over area. Tensile strain, change of L over L naught. Second, shear stress and shear strain. When an object is subjected to a force parallel to one its faces while the opposite force is held fixed by another force. Shear stress, F is parallel over area. Shear strain, X over H, tan phi. Volume stress and volume strain. Volume stress is stress wire causes when volume deformation on an object. Volume stress, change of F over A, which means change of P. But a volume strain is change of V over original volume. Now, let's go to another examples and their following here, which is measure considerable with. Elasticity moduli or elastic modulus. The stress will be proportional to the strain if the stress is sufficiently small. The proportionality constant is known as elasticity moduli, elastic modulus. Stress is directly proportional to strain. Stress, which is equal to elastic modulus times strain. Rearranging the equation, elastic modulus, which is equal to stress over strain. Corresponding to the three types of strains, there are three types of elastic modulus: Young's modulus, shear modulus, bulk modulus. Young's modulus is the resistance of a solid changes in its length, y which is equal to F over A over change of L over L naught. Shear modulus is the measure of resistance to motion of plane solid sliding each other. Third, bulk modulus measure the resistance of solids or liquids change volume, V which is equal to minus change of P times V naught over change of V. Worked example 3.1. Suppose the cable 940 as the actor reaches lowest point. What diameter should 10-meter long steel wire have if we do not want to stretch 0.5 centimeter under these conditions? Use the Young modulus of steel 20 times 10 to the power of 10 Pascal. Solution. Use the Young's modulus equation y which is equal to f over a over change of L over L. Then rearranging the equation a which is equal to f over y over change of L over L naught. F over y divided by change of L over L naught. Now, if we divide it, then multiply and change the fraction. F over y times. If the change of L over L naught, if we become multiply, change the fraction. L naught over L, change of L. So we can determine like this way. Worked example 3.2. A solid brass sphere is initially surrounded by air and the air pressure exerted on it 1 times 10 to the power 5 Newton per meter square. The sphere is lowered into ocean depth where pressure is 2 times 10 to the power 7 Newton per meter square. The volume of a sphere is air is 0.5 meter cube. By how much does this volume change is submerged? Use a bulk modulus equation. B which is equal to change of minus change of P over change of V over change of V naught. B which is equal to minus change of P times V naught over change of V. Now rearranging the equation, change of V which is equal to minus change of P times V naught over B, which is equal to minus 2 times 10 to the power of 7 minus 1 times 10 to the power of 5 times 0.5 over 6.1 times 10 to the power of 10, which is equals to change of V which is equal to minus 163.1 times 10 to the power of minus 6 meter cube, and also approximately minus 1.631 times 10 to the power of minus 4 meter cube. Let's go to 3.3. Density and pressure and static fluids. Density is the derived quantity that depends the ratio of mass per volume. Change density, rho, which is equal to m over v. SI unit of density is kilogram per meter cube. A specific gravity is the ratio of the density of substance to density another substance standard, which means density of substance over density of water. Listen, specific gravity is unitless quantity. Worked example 3.3. A solid sphere which has radius 0.1 meter. The specific mass is 1 kilogram. Find the density and the specific gravity. To find the density, let us calculate the volume of a sphere. The radius 0.1 meter is given and the mass 1 kilogram is given. Calculate the volume of sphere to determine the volume. Use the volume of sphere V which equals to 4 over 3 pi r cube. V which is equal to 4 over 3 pi 0.1 meter the whole cube. V which is equal to 4 over 3 times 3.14 times 0.13 the whole cube, which is equal to 4.18 times 10 to the power of minus 3 the meter cube. Use the density equation. Now we find the volume. Now let's determine the density. Density which is equal to 1 kilogram over 4.18 times 10 to the power of minus 3 meter cube, which is equal to 239 kilogram per meter cube. Use the specific gravity equation. The density of substance is we got here 239 kilogram per meter cube, and the density of water 1000 kilogram per meter cube. Let's determine them. 239 kilogram per meter cube over 1000 kilogram per meter cube, which is equal to 0.239. Pressure is the ratio of force to the cross-sectional area. The SI unit of pressure is Pascal. 1 Pascal is equal to 1 Newton per meter square. The pressure produced by the column fluid of height h and density rho is given by P, which is equal to rho gh, where h is depth, g is acceleration due to the gravity. So absolute pressure is the total amount actual of point. Worked example 3.4. A submerged wreck is located 18.3 meter beneath the surface of the ocean off the coast of South Florida. Find the gauge pressure and absolute pressure. Solution. Use rho density of seawater 1025 kilogram per meter cube and atmospheric pressure 101.3 kilopascal. Use the liquid pressure P which is equal to rho gh equation. P gauge which is equal to rho gh 1025 kilogram per meter cube times 10 meter per second square times 18.3 meter, which is equal to 182 kilopascal. Totalize the sum of gauge pressure and atmospheric pressure to get the absolute pressure. P absolute is equal to P gauge plus P atmospheric 182 kilopascal plus 101.3 kilopascal, which is equal to 283.3 kilopascal. 3.4. Buoyant force and Archimedes principle. Pascal's principle states that pressure applied to a confined fluid and a container is transmitted equally to all regions of the fluid and the wall of the container. An important application of Pascal's principle is hydraulic press. Archimedes' principle states that when a body is completely or partially immersed in a fluid, the fluid exerts an upward force on the body equal to the weight of the fluid displaced by body. A buoyant force, which is called weight of displaced fluid, FB, which is called to MFG, FB, rho F, VFG. Worked example 3.5, a sample of unknown material 300 Newton in air and 200 Newton submerged in alcohol solution of 0.7 times 10 to the power of 3 kilogram per meter cube. If we determine, let's subtract them and let's calculate them. And the last unit, fluid dynamics. Flow rate is the quantity of liquid flowing per second through section a pipe. Flow rate, which is equal to volume over time, which means area times heat over time. So, heat over time means velocity. Flow rate, which is equal to AV. Equation of continuity AV, which is equal to constant A1 V1, which is equal to A2 V2. Bernoulli's equation, the sum of pressure, kinetic energy per unit volume and gravitational potential energy per unit volume has the same volume value at all points streamline. They are constant. We can use the equation the following, which is given by Bernoulli's equation or by using the Bernoulli's principle by determining the equation of